Hello, welcome back. So in this video we are using Quartus Prime to program a FPGA from Intel. It's a Max 10. So this program is a motor control and we are using these three libraries as usual. The STD Logic 1164, the STD Logic ARITH and the STD Logic Unsigned. So the provide VHDL code details the implementation of a state machine base for a motor control system on Intel Max 10 FPGA using the Quartus program. So first of all, we have the entity declaration of the motor control. This section declares the inputs and outputs of the control system. So the inputs consist of the 50 MHz clock signal, the reset signals, and the direction signal. Outputs include the clock input signal and the control signals for the motor. So now we have the architecture. This is the state of the machine. So basically, the architecture section describes the behavior of the motor control system. It initiates with the control divider process to generate a slower clock. So it will be the clock new, and is synchronized with the input clock of 50 MHz for controlling the state transition. So I'm using 0 here for simulation purposes, but when I want to use this code for the physical part, I will have to put here, for example, a 23, because if I have a number around 25, it will be slower, and you can actually see how it's moving the motor control. But if I put something lower, it will be more faster. So I recommend to use a higher number. The maximum number, as you can see, is 25. So keep it in mind. Now we have the process that generates a slower clock by counting a clock cycle of the input clock. So if it resets the clock counter when the reset signal is assert and increments the count on each rising edge of the input clock. The slower clock input is the clock new, is then assigned to the output port CLK for the motor control operations. Now, the combinational processes, or the process. This process defines the state transition and outputs of the motor control system based on the present state. It employs a case statement to specify the motor control signals of each state, considering the direction input of the direction for forward or reverse motor operations. So as you can see, if the direction is set to 0, it will go from 0 to 7, and it's machine state, as you can see. But if the state is set to 1 or the reverse, it will be from 0, 7, 6, 5, 4, 3, 2, 1. So I'm gonna show you from here. As you can see, this is the RTL viewer, and if I double click here, this is the state machine, and as you can see, it goes from 0 to 7 to 1 to 5 to 6 to 4 to 3 to 2. It will be like that. So for example, if the direction is set to 0, it will go from 0 to 1 to 2 to 3 to 4 to 5 to 6 to 7, and else it will go from 0 to 7 to 6, to 5, to 4, to 3, to 2, to 1, and to 0. So now I'm gonna explain the VHT. So here we are using this loop, and as you can see we have these three declarations. So direction is set to 0, reset is set to 0, and RST is set to 0. This is only for simulation purposes, and well, within the begin and the end block, so this part, there's a loop. This loop is called CLK loop, indicating a repetitive sequence of instruction. This loop iterates indefinitely, continuously generating clock pulses according to the specified time. So within each iteration of the loop, the clock signal of 50 MHz is first set to 0, as you can see, representing a falling edge. This transition marks the start of a new clock cycle. Following this assignment, the process halts execution for 10 nanoseconds using the wait for statement. So here is the wait for statement of 10 nanoseconds. This process halts execution for 10 nanoseconds using the wait. This delay simulates the duration of the low phase of the clock cycle. What do I mean with low phase? This is the low phase, this is 0. Now, subsequently, the clock signal is set to 1, indicating a rise edge, which signifies the end of the low phase and beginning of the high phase. This is the high phase, this one, of the clock cycle. Another wait for the statement is used to introduce a delay of 10 nanoseconds, as you can see, representing the duration of the high phase of the clock signal. Now, the loop then continues in execution, repeating the process to generate a subsequent clock pulses. As there are not exit conditions specified within the loop, it iterates indefinitely, continuously producing a square wave clock signal with a period of 20 nanoseconds, within 10 nanoseconds and also at 10 nanoseconds. This clock generation process is crucial in digital circuit design and simulation, as it provides a stable and consistent clock signal necessary for synchronizing operations within the circuit, in FPGA and also in ASIC designs. So I hope you learned something from this part of the code, and let's jump for the physical part of this motor control.
Hi everyone, today we're gonna see the step motor with the FPGA University program. We have the step motor with a driver there, and we're using a 245 buffer so that the 3 volts of the well, is to keep safe the FPGA, right? So we're using that buffer, and of course we have an external voltage source connected to the breadboard, I mean, and well, that's it. So now it's running perfectly fine. We have here an input so that the step motor stops. Let me pull it up. As you can see, the step motor stopped because I pulled this switch up, is the switch number 0, and if I pull it down again, it's going to keep working. It's moving, as you can see. Now the let me see, this switch, the switch number 3, is going to switch directions. So if I pull it up, it's going to go to the opposite direction. So I'm going to do that so you can see, and it's moving to the other way. And if I pull it down again, it's going to go to the direction of, well, the original direction. And we can do combinations. So let me put stop there, and I'm going to switch directions. So once I switch down the first switch of the stop, it's going to move to the other direction. So there you go. And if I put down again the switch of the direction, is going to go to the original direction. And that's everything. So the materials we were using are a 245 buffer. Those are the connections. We are connecting the GPIOs of the FPGA. We're using the outputs 0, 1, 2, and 3. Those are the first ones in the pin planner. And that cable, that white cable right there, is the GND, and that's the pin 12, I think, of the FPGA. So we have common GNDs here. Now these over there that are connected to the outputs of the buffer are the Bs, B1, B2, B3, and B4, and those are connected right into the driver, as you can see there. There you go. The blue one is the in 1, the green one is the in 2, the yellow one is the in 3, and finally the orange one is the in 4. And what else? Well, we are connecting the enable to GND, and we are connecting the dir or direction to BCC in order to have A to B, so that the inputs are A and the outputs are B. Ignore those resistors. I was just trying to figure out why my project wasn't working, so I connected two LEDs on those on the cable blue and on the cable that is on the A1, the yellow one. And finally, it was because the buffer wasn't working, so I just switched it up to one that actually works, and voila, everything was working perfectly. And another thing to keep in mind is that you have to connect the GND and BCC of the driver right into the board. So that we. Another thing to keep in mind is that you have to connect the GND and BCC of the driver right into the board. So that we have common GNDs and the driver is connected to the another voltage source. So that's everything. Thank you so much for watching this. See you in the next one.